Hello there. Can you hear me? No.
I can hear you.
That's good.
Again?
Hello, Jimmy.
Good to see you here.
Hello.
Ooh, bad echo.
Got a bad echo here.
Yeah. All right.
Do you mind speaking again?
Which one of us do you want to speak?
Yeah, that's better. I think it's settled down. Okay, everybody that I have joining has joined. So it's your show. And then we'll come back with any questions or concerns that we may have. So I don't plan on interrupting the slide presentation. We'll do that at the end. Okay.
Okay, sorry. I heard everything you said. We were just getting ourselves lastly set up with all our audio to make sure everything there was good to go. So
Okay.
Perfect. So no questions in the middle. So we will just run through the presentation then. And okay, so first of all, my name is Megan. I have been the one doing the communicating with you, so it's great to meet you. And we are Swan Punch Rocket Team from the team University of Florida. So I'm just going to start by introducing our team a little bit. So we are competing in the 10,000-foot commercial off-the-shelf category. This is just an introduction to our team leadership. You're going to hear from almost all of these people today. So our team is structured managerial, and then we have vehicle design leads, payload design leads, and then a manufacturing lead. So I serve as both the project manager and the chief engineer for the team, and then all of the technical leads are listed out there, and you're going to hear from all of them about their various systems today and see their projects. So just an update before they start talking about where our team is at. We have, of course, submitted all of our progress reports and paid all our fees for competition and submitted the frequency allocation form. We have performed a test flight, and we are now completing our video conference. In terms of preparing for competition, we've coordinated our roster and our travel. We've secured our motor, and we're currently in the process of working on the technical report for submission. So we're excited for all of that. And with that, I will pass it on to our technical leads to start talking through the project.
Hi, I'm Dustin. I'm the structural design lead for IREC. Just starting off with some basic dimensions and stats about the rocket. We chose to go with a single stage rocket for our design. It's a 6-inch diameter rocket, so it has an inner diameter of 6 inches and an outer of 6.14. We went with a 4-fin design. Our vehicle length is approximately 127 inches. Our vehicle weighs 42.2 pounds without the motor. And the vehicle weight with the motor is about 60 pounds. For the airframe of the rocket, it's actually student research and designed carbon fiber that we made in-house. We made it using a 3-ply symmetric layup consisting of 2 3K biaxial carbon fiber sleeves with a middle ply of 12K unidirectional carbon fiber. We used Solar Composites 820 resonant hardener system for our epoxy of choice. We conducted the whole thing on a polycarbonate mandrel, and then we wrapped the entire wet layup, in a silicone PET tape in order to avoid sticking with the adhesive. And that essentially simulated a vacuum bag, because vacuum bagging such a large airframe was difficult. And then we cured it over 3 days using an insulated curing chamber and a heat lamp. And overall, our airframe consists of 2 4-foot sections that are 6 inches in diameter, in addition to a 1-inch switch band that's also comprised of the same carbon fiber. For our nose cone, we just chose an off-the-shelf fiberglass nose cone. It is aluminum tips to improve flight stability by moving the CG a little forward and strengthening the nose cone. It is a 6-inch diameter. We have it right over here. And it is a 5-to-1 von Karman, which we chose for ideal aerodynamic performance. for flight regimes above 0.8 Mach. And then we have the nose cone shoulder, which we have right here. This joins the nose cone in the forward airframe. It's also off-the-shelf fiberglass, 6-inch diameter. Fits nicely inside of the nose cone and the forward airframe, 9 inches in length, and it's fastened via 4 nylon shear pins, which pass through the airframe. Our avionics bay, which we have right over here and houses the avionics sled, joins the forward and aft airframes. It's also made of the same off-the-shelf fiberglass, 6 inches in diameter. It is 13 inches long and fastens via 3 plastic rivets to the forward airframe and to the aft airframe via 3 nylon shear pins. Moving on to the forward bulkhead, which is situated right here inside of the previously mentioned nose cone shoulder. It seals the forward aft away from the nose cone. It serves as a point of attachment for the recovery harness via stainless steel eye bolts, which can be seen right there. It additionally serves as an attachment point for the GPS mount, which you can see right there on the slide. It is housed in the nose cone to avoid signal interference because the radio signals have issues passing through the carbon fiber airframe, so they need to sit inside of the nose cone to receive signals properly. It is made of student research and design PVC, and we made it simply by turning it down on a manual lathe, boring out that center hole so that we could mount the GPS, which is a PET-G 3D printed part. And we bored out the center hole and then parted it from the stock. The avionics bay bulkheads seal between the avionics bay, keep them from ejection gases. If you would like to hold that up so I can see it. Not on freehand. This seals the avionics bay from harmful ejection gases. It serves as the point of attachment for the recovery harness, once more via stainless steel eye bolts. It serves as a mount for the CO2 ejection system, which we'll elaborate more on later. It is student research and designed aluminum 6061, manufactured via turning down the size on a manual lathe, parting, drilling the holes. And then our fins, which we have a couple of right here. These are student research and designed epoxy glass fins. We cut them ourselves on an abrasive water jet. We chose epoxy glass as our material of choice for its strength in both torsion and bending. It also has adequate strength to withstand impact on ground hit. We chose it over metal just for weight purposes because metal fins, whether aluminum or steel, would be much, much heavier than a composite fin, and overall improved stability as well. We went with a 0.192 inch thickness for these fins, which was deemed adequate to withstand all flight loads, and it was cut from bulk sheet material. Once more, on a water jet, 4 fins was chosen over a 3-fin design for stability advantages. All right, moving on to discuss the aft assembly, which was our initial concept for the design this year. Our main goal was to produce a design that could be easily disassembled and reassembled with no damage to the components. This is in contrast to a traditional epoxy aft, where everything is essentially secured during assembly, and once you have everything in place, nothing can really move. It allows for easy design iteration post-assembly. If you need to change a part, you can. If you want to make any adjustments after the fact, you're not stuck with what you have. The components can be replaced in the event that they're damaged during launch or testing. And then you can also reuse those components for a future project or for future vehicles. And the disadvantage that comes with that is higher manufacturing costs, because aluminum parts to be machined both cost more in terms of raw material and take more time to machine. And there's also a potential weight disadvantage because you're going to have much, much more weight with this entire metal skeleton versus just wooden epoxy. The fins are actually mounted via attachment to these 2 exterior fin brackets that you see here that look just like this. You can see as they sit on the outside of the fin design, they are through the wall, so they pass through the fins and fasten via 4 stainless steel flathead screws. And then each of the fins is also press fit into a radial slot in the centering rings. And then the brackets are fastened through the airframe to all of the centering rings once more via stainless steel fasteners. And then our motor casing of choice was the 98 millimeter off-the-shelf aluminum motor casing from Aerotech. And here we have some larger pictures so that you can see what it looks like. The left is the full assembly with just a single fin so that you can see how everything sort of fits together. And then the right side is actually the view from the bottom of the rocket of the entire assembled structure. The previously mentioned fin brackets are made of 6061 aluminum. Each bracket was machined on a CNC mill from a 13.5-inch bar stock, 1 by 1 inch. All the surfaces that were tangential to the airframe sat at an 8-degree angle from normal. So because of that, they had to be machined on a custom 3D printed fixture. All of the brackets came out to 13.25 inches after machining. And for the left brackets, there were simply 4 countersunk holes that once more allowed the left bracket to fasten to the right. And then the right had the threaded holes, which allowed it to be secured. The centering rings are Student Research and Design 6061 aluminum. They were manufactured by cutting bulk 1/4-inch thick plate on abrasive water jet to get the overall geometry. And then to make each of the exterior threaded holes that you see there, they were machined manually on a rotary chuck. The aftmost centering ring, so there's 4 centering rings in total. The 4th one, which sits on the back and fastens to the thrust plate, differs from the other 3 in that it omits the fin slots in favor of 4 threaded holes. The thrust plate and motor retainer subassembly was a Student Research and Designed in-house aluminum design consisting of the thrust plate, an off-the-shelf motor retainer from Aeropack, the 6061 aft centering rings, 12 stainless steel button head screws, and 4 stainless steel flathead screws, which were longer and fastened the aft centering ring. That is this subassembly that you see right here. Next slide. And for the thrust plate, we chose to make it once more out of 6061 aluminum. We cut it from a bulk 1/2-inch plate to get the overall geometry and then machined the detailed features on a CNC mill. It features a 6-inch diameter shoulder for mounting into the aft airframe. The entire design slides very nicely into the back end of the rocket and then sits there. It features a recessed pocket to easily align the motor retainer. So as can sort of be seen right here, the motor retainer actually fits very, very cleanly into a pocket there, which makes assembly quite simple. It has 12 threaded holes for fastening the motor retainer to the thrust plate itself, an additional 4 to fasten the thrust plate to the aftmost centering ring. Now, this entire aft concept that we were initially going to use for the competition vehicle was tested during test flight and experienced material failure. We are still investigating the potential modes of failure that occurred and developing a narrative to figure out exactly what happened. At the moment, though, we are choosing to rebuild our aft with a new concept, going with a traditional epoxy aft design. The fins from the initial concept are reused because they didn't sustain any damage during the test launch. The aluminum brackets and centering rings are omitted in favor of epoxy glass rings, which we mounted via epoxy to the airframe and motor tube. The aftmost centering ring is no longer aluminum. It is now made of 1/2-inch thick wood. And the epoxy fillets are used to mount the fins to the airframe in place of the existing metal brackets. And the design now features a motor tube, which our initial design did not have, that is 4.02 inches in outer diameter, made from G12 fiberglass. The thrust plate and motor retainer also did not sustain any damage during the test flight, and so those will be repurposed. I'm now going to pass it off to Colton, our flight dynamics lead.
I'm Colton, as Dustin said, the flight dynamics lead. The motor we decided to choose was a commercial off-the-shelf Aerotech M2500 motor with an average thrust of 2,500 newtons, a total impulse of 10,240 newtons, and a burn time of 3.9 seconds. And you can see a thrust curve pictured. We ran some flight simulations for the modular aft rocket design using the latest open rocket software that came out to an apogee of 10,180 feet, a velocity off rail of 104 feet per second, a thrust to weight ratio of 7.8, max velocity of 1,037 feet per second, a max acceleration of 335 feet per second, a static margin of 2.7, and using a ballast mass of 1.5. And we have a plots of position, velocity, and acceleration throughout the flight plotted for you. And the next slide is a plot of the stability throughout the flight. We also ran a simulation with using the new epoxy aft design with an apogee that's very close to 10,000 feet, 9,996 feet, with a velocity off rail of 104 feet per second, a thrust weight ratio of 7.8, a max velocity of 1,010 feet per second, a maximum acceleration of 325 feet per second, a static margin of 3.38, and this is using a ballast mass of 2 pounds. And again, the position, velocity, and acceleration for the flight are pictured. And the next slide is a plot of the stability throughout the flight. Hang off to Khan.
Hello, everyone. My name is Khan. I'm the avionics and recovery lead. So the flight computers that we chose for our rocket are off-the-shelf Stratologger SL100 and Stratologger CF because we've flown these flight computers numerous times and they've been really reliable to us. And these flight computers are powered by 2 separate 9-volt batteries, which are wired to the altimeter separately for redundancy purposes. And they are armed and disarmed through 2 micro switches that are mounted on the avionics sled, which we can see it on the picture, and also we have it here built. These switches work. They arm and disarm through a pin plunger system where when we insert a pin through these switches, the system is open, and when we pull out the switch, the system is closed and electronics are armed. The recovery hardware that we're using to recover the rocket are a 36-inch standard rocket man parachute as the drogue parachute, 96-inch Iris Ultra standard parachute as the main parachute, and 2 flame-resistant parachute protectors around each parachute to keep them from burning and also keep them organized inside the airframe. And the hardware that we're using to attach these parachutes to the rocket are 5/16-inch D-links, swivels, 3/8 steel eyebolts, and 1/2-inch Kevlar shock cord, where we have 40 feet of Kevlar shock cord in each section, which is roughly around 3 times the length of the rocket. Here we can see the layout of the recovery hardware, where we have the eyebolt on one end, which is connected to the 16 feet of shock cord via D-link, and after 16 feet of shock cord, we have the parachute protector, another 11 feet of shock cord, a D-link, a swivel, which connects the drogue parachute to the shock cord. We have another 13 feet of shock cord, which connects to the nose cone eyebolts via another D-link. And we have the payload that is also tethered to this shock cord line, which the payload team is going to talk more about how the payload deployment sequence works. And for the aft recovery layout, we have a very similar looking layout. Instead, we just don't have the payload, but everything else is pretty much the same. So the drogue deployment happens at apogee. Like I said, the 36-inch Rocketman parachute via 3.5 grams of black powder, which gives us a descent speed of 85 feet per second. And under the drogue parachute, we're expected to drift about 0.25 miles with average wind speeds in Las Cruces at the time of the year. And the main parachute deploys at 800 feet along with the payload via 34 grams of CO2. The reason why we chose CO2 is because we wanted the payload was not contained in a sealed environment inside the rocket, and we didn't want to damage the payload during the ejection event. So we just chose a cold ejection instead of a hot ejection. And under the main parachute, the descent rate of the rocket is 20 feet per second, which is safe landing speeds. And we have 0.1 miles of drift radius underneath the main parachute. And we have the total drift of 0.35 miles over 145 seconds. And the CO2 ejection system was student design and research, and it was initially the idea was found through looking at different off-the-shelf available CO2 ejection systems, and the system that we chose to build is we can see the picture on the top right where we have a black powder housing, a puncture piston, a spring, and the combustion chamber where everything comes together, and the black powder sits inside the black powder housing. And when that black powder is ignited, it accelerates a puncture piston and hits the CO2 cartridge, breaking the seal and releasing the CO2. We can see the cross section on the middle picture right there. And all these components were machined out of bar stock aluminum 6061, and the assembly, the CO2 ejection assembly, is mounted on the avionics bay bulkheads, and they face towards the forward section of the rocket since they're the main, since they deploy the main parachute and the payload. And the GPS that we're using to track our rocket after launch is a tele-GPS. It's located, like Dustin mentioned earlier, inside the fiberglass nose cone. It uses a 70 centimeter transmitter with 10 milliwatts of radio frequency output. We're going to be using 434 750 megahertz as our frequency. And this GPS is powered by a 3.7 volt LiPo battery. And we receive the radio frequency from the GPS through a teledongle antenna, which connects to a computer and matches this frequency as the GPS. And using the manufacturer application that is provided to us by the manufacturer, we can track the rocket and find its location on the map, and we can get the coordinates as well. So far, before having our test launch, we've tested all the recovery events, and first we tested the flight computers, where we tested functionality using the manufacturer's software, where we fired the drogue charge, fired the main charge, but instead of having black powder charges at the end, we connected LED lights to see if they were going to light up, and everything worked out. After that, we've tested the CO2 ejection system outside of the rocket before we actually put it together to see if it was going to puncture the cartridges reliably and how much black powder it needed. And after we got it to work, we've tested the whole system, putting it together, where we tested the main deployment and the payload deployment events, which we can see the pictures on the right. And 34 grams of CO2 cartridges were sufficient for a reliable deployment. And for the drogue deployment, you can see a picture on the top where we used 3.5 grams of black powder to separate the aft from the avionics bay and deploy the drogue parachute. And the backup charge for the black powder is going to be 20% more, which is roughly around 4 grams for the backup charge, which is going to be connected to the backup altimeter. And the CO2 backup charge is going to be the same amount of CO2, but they're going to be going off very close to each other to where it's going to work as a backup charge. And I'm going to pass it off to Jason.
Hi, I'm Jason Rosenblum. I'm the payload software lead, and our payload this year is an autonomous quadcopter, which will be aerially deployed after the main ejection. And its goal is to take images of the launch vehicle's landing site after it's landed. This is the drone right here. It weighs 3.8 pounds, and each motor has a thrust of about 1.8 pounds, which results in a thrust to weight ratio of just under 2:1. It's powered by a 4,000 milliamp hour LiPo battery. Its main sensors are a GPS, inertial measurement unit, barometer, and an ultrasonic sensor. And it communicates with a ground station using an XP Pro S3B. It is made out of student researched and designed carbon fiber custom carbon fiber layups for both the frame and motor arms. And the payload has 2 GPSs, one which is on the quadcopter itself, which is a U-Blox Max M8Q, which uses the XB Pro S3B 900 megahertz frequency to send the coordinates back to the ground station. And the parachute has its own GPS, which is a off-the-shelf Big Red B 900 megahertz.
Hello, everyone. I'm Joseph Pinkston. I'm the payload mechanical lead. Our quadcopter in its flight configuration has a total length of 17.5 inches, a propeller tip to propeller tip width of 21 inches, and a height of 4.5 inches. When we have the quadcopter in its stowed configuration inside of the launch vehicle, it has the same length and height. However, the width shrinks down to 4.5 inches as the quadcopter arms can be folded inwards. So for the main, as Jason mentioned, the main structural components for the quadcopter are the top and bottom frame and the arms that connect the propeller motors to the quadcopter frame. These components are all student research and design carbon fiber. We used 12 ply prepeg symmetric layup, and this was vacuum bagged and cured in an oven over a 4-hour cycle. And then the components were then cut from this layup on a Omax water jet. And these are a picture of the components when they came off of the water jet. So for the quadcopter mechanical components, as mentioned before, the quadcopter is able to be folded, the arms are able to be folded inwards for flight configuration. This happens for the unfolding mechanisms, which are located at the 4 corners of the quadcopter frame, which connect the propeller arm motors to the actual quadcopter frame. These unfolding mechanisms each one has a 180-degree torsion spring, a pin plunger locking mechanism, 2 nylon thrust bearings to help carry the load to the frame itself, and they have a pivot housing, pivot chamber, and a hard stop, all of which are 3D printed using PETG filament. The arms are able to be folded inwards using the pin plunger system, and so when you pull the pin, the arm can fold inwards, and then after releasing the arms during deployment, they snap open, allowing the drone to begin its flight configuration. We also have on either end of the quadcopter, we have the container deployment rack and pinion system. These are located at both ends of the quadcopter. These are what allow the quadcopter to be deployed from the container, which will be spoken about later in the retention system section. These each have a DC motor. It's a driven rack and pinion system. It has an aluminum beam, which helps carry the load, a steel pinion and acetal rack. And when these rack and pinion systems are going to be actuated, they will be experiencing a 2-pound load. These were tested and were able to open and actuate under 8-pound loading, and these were also utilized during the test flight. Then the last assembly on the quadcopter is the parachute deployment rack and pinion. This is located at the top of the center of the top frame, allowing the quadcopter to be attached to its parachute directly above its center of mass, giving it its most stable location for deployment. This is also a very similar system to the DC motor driven rack and pinion. However, it has a more structurally, a stronger component for the rack and pinion housing, as well as the hard stop, as this rack and pinion system will experience a 5-pound load during actuation and has been tested on the ground. And now I'll hand it over to Lisa.
Hello, I'm Lisa. I'm the payload electronics lead. And for our quadcopter, we used a PCB to improve wire management and to make sure that no wires would come loose during the actual flight of the drone. So on the right, you can see a Altium schematic, which includes all of our sensors that are going to be present on connected through the PCB, and the PCB is used to provide electrical connection for all of the components. So some of the sensors and actuators included on the PCB include our MTI-7 IMU, to which is connected a barometer and the GPS. Additionally, we're going to have an ultrasonic sensor, which is going to be mounted externally with line of sight to the ground that can help to detect landing of the drone. Additionally, we have an active buzzer to confirm the proper working of all the electronics. And we have a XBRF module, which will be communicating with a ground station and sending coordinates of the drone back. We also have 3 DC motors for deployment, which are also external, and we have an external button to arm all the electronics from outside. So the microprocessor that we chose was the Raspberry Pi 02W because of its small form factor and also its compatibility with the project. Additionally, we have an electronic speed controller, which was used to control 4 brushless 1300 kV motors. And we chose these motors because they could provide the drone with the 2-to-1 thrust to weight ratio, which it would need in order to be stable and to sustain itself during flight. Additionally, all the electronics would be powered with 4,000 milliamp hour LiPo battery, which would provide the drone with optimally 5 to 10 minutes of flight time. And the PCB would be mounted on the top frame of the drone and help in managing the connection between all of these components. I'm handing off to Joseph again.
So for the payload deployment sequence, the quadcopter will be stowed inside of the forward airframe of the launch vehicle inside of its container. The specifics of the container will be discussed in a future slide, but this is the fully built container here. These both are stowed inside the forward section of the launch vehicle, and then during main deployment, the quadcopter and the container are deployed with main, and the container is tethered from the main recovery harness as seen in the image. At an altitude of 600 feet, the quadcopter will be deployed from the container and will descend under its 36-inch parachute. During this time, the quadcopter will do some system checks to ensure all of the software is operating nominally. And once we have given the manual go-ahead for the quadcopter to release, the quadcopter will release from its 36-inch drone or 36-inch parachute and will begin its flight operations. And I'll hand it over to Jason.
This is a flow chart of the steps the software goes throughout flight. First, once the payload is armed on the launch pad, the IMU will wait for acceleration to determine launch. Once launch is detected, it will wait, and using both the simulation timing and the barometer data, it will look for the CO2 ejection. And once it has detected that ejection, it will use the barometer and GPS altitudes to release from the container at approximately 600 to 700 feet after the main ejection, which is at 800 feet. Once it released from the container by actuating the 2 DC motors on both ends of the drone, it will descend under a parachute first. While it's descending under that parachute, as Joseph mentioned earlier, the payload will check the sensors to ensure they're within proper limits, such as GPS limits, altitude limits, and make sure the acceleration and velocity are within expected bounds. Once it's completed those checks, the team from a ground station will send a command giving it the go-ahead to release, just in case the payload drifts somewhere where it's unsafe to release from the parachute. It will not release on its own. And once it's given that command, it will wait for an appropriate altitude, which is, we have a maximum 400 feet limit on that altitude to release from the parachute. If the release command is given, it will release from the parachute and immediately autonomously avoid the parachute to ensure that the parachute doesn't drift back into the drone and enter an autonomous control sequence. During that sequence, it will follow GPS coordinates, which are communicated by the ground station to where the launch vehicle is located, take its pictures. Once it's taken its pictures, it will descend for landing, where during that descent, once the ultrasonic sensor receives good data, which is at about 1.5 meters above the ground, it will transition to that ultrasonic altitude for finer altitude data, and touch down and turn off all motors and activate a buzzer that's on the drone to make it easier to locate. If during the autonomous flight, the drone starts to go somewhere unsafe or any obstacles need to be avoided, the ground station can take manual control of the drone to initiate either an emergency landing, some obstacle avoidance, or emergency shutoff of the drone. And then in the case that the parachute is not, the parachute release command is not given, it will simply descend under the parachute and land on its own.
So for the payload retention system, it consists of a couple different assemblies. The assembly that is currently inside of the forward airframe and is always remains with the forward airframe is the 8020 rail assembly. The 8020 rail assembly consists of 2 concentric airframe mounts, which are 3D printed out of PETG. These allow the two 1-foot 8020 T-slotted extrusions to line up perfectly concentric with the airframe. And then these 80-20 extrusions are then attached to the concentric airframe mount, which has 2 aluminum bar supports through 4 90-degree corner brackets and fasteners. This assembly is currently inside of the forward airframe, and it's mounted through 4 ⅛ screws through the outside of the airframe. And then onto this assembly, the 16-gauge steel container, which can be seen right here, is what slides onto that 80-20 rail assembly. This container is 22 inches long, 16-gauge steel. It has 2 retention mounts. These retention mounts are located inside of the airframe. You can see one right here and then one up here as well. These are 3D printed out of PETG as well. These are what the 2 rack and pinion assemblies on the opposite ends of the quadcopter. Those are the 2 mounts that the quadcopter attaches to. And so those mounts have 2 cutouts that allow the beams to slide into those mounts. And then the last component on the inside of the inside of the container is the parachute shield. This is a 3D printed component as well. Under it is where the 36-inch parachute and its ballast mass are located. This parachute shield is what keeps the parachute from deploying from the container prematurely while the quadcopter is still inside of the container while under the main parachute. And then to allow the container to slide onto the 80-20 rail assembly, there are 6 linear slides that are located on the bottom. You can see them here. They're white. These are made of a high strength polymer. These fasten directly to the container and allow the container to slide onto the 80-20 rail assembly. And then the last component on the bottom of the container is that recovery harness mount. That mount is welded to the bottom of the container, made of steel, and connects the shock cord of the container to the main recovery harness. So these are 2 images of the payload and container the day before the test flight. It shows the quadcopter inside of the container. You can see one of the aluminum beams engaged with those retention mounts inside of the steel container. And then you can also see the 36-inch parachute that is folded under the parachute shield. This is the configuration that was flown on the test flight. And we were able to recover both the quadcopter and all of the retention system components without any major structural damage on them. And this is an image that shows the payload under the parachute. We weren't able to see any images of it during the flight as the system was too far away during the test flight. However, this is what the simulated system looks like. We have the parachute shroud line connection, which connects to a shock cord. This shock cord then has a ballast mass and the GPS that is attached to the parachute for tracking the parachute. And then that shock cord mounts to the parachute deployment rack and pinion that is on top of the quadcopter top frame. And when the parachute deployment rack and pinion is able to be actuated, it allows the shock cord to disengage from the quadcopter, and the quadcopter is able to begin its flight.
This is a list of some of the tests we've completed for the payload. First thing we did was we tested the thrust of the motors, which is shown in the top left image, the result of this was we found around 1.8 pounds of thrust. The next few tests are all related to the release from the container, which was the rack and pinion testing, unfolding mechanism testing, pin plunger locking testing, and retention system testing. So that all proved that the arms could lock properly and securely, and also that it could release from the container, that the DC motors could actuate and release it from the container. We also, with the avionics and recovery lead, tested the ejection, the CO2 ejection, and which proved that the sensors would remain undamaged during ejection, as well as while the drone and PCB were being finalized, we 3D printed a mock-up prototype of the drone shown in the top right and began controller tuning with it on a 80-20 test stand using a rod which went through the center of the prototype. Using this, we were able to prove that the drone could be tuned using our software. Then we did controller tuning with the final quadcopter shown in the bottom right on the same 80-20 stand. And this time we included bearings on it to decrease the friction from the rotation. We also conducted a 30-minute idle battery test to show that the battery would not drain too quickly while idle. And then also a 5-minute 75% throttle battery test to prove that the battery could power the drone for at least 5 minutes of flight time. As well as the bottom left shows a oscilloscope probing of the Raspberry Pi as it sends a D-shot command to the electronic speed controller. We're communicating with the speed controller using a method called D-shot, which uses is a packet of high and low signals shown in the bottom left, and that was our custom implementation testing.
Oh, good.
So as was alluded to previously, when we conducted our test flight, the modular aft system did experience catastrophic material failure. The time of failure during the launch is uncertain. It is believed to occur shortly after the initial off the rail. It is believed currently that the force of the motor induced an aerodynamic load on the fins that caused shearing in the centering rings due to inadequate reinforcement, and that one of the fins failed in this way, came apart from the structure, and then resulted in bending of the brackets. There was limited deformation of the brackets as a whole. Out of the 4 sets of brackets, 2 of them are almost entirely undamaged. There was significant bending deformation of the center rings, as well as shearing in several locations. There was no deformation in any of the fasteners or the thrust plate subassembly. The material failure of the airframe appeared to occur primarily in locations where the centering rings also failed, suggesting that it was the result of cascading failure due to the initial shearing of the centering rings, and then abnormal loading from the fins being an awkward configuration. The front end of the airframe also experienced some zippering, which at this time we're not sure as to the exact reason for that. And one of the fins actually experienced some buckling with the airframe, which we're still developing a theory of failure for that. The fins experienced no deformation whatsoever, so we'll be reusing those for use in the competition vehicle. And the same thing is true of the thrust plate and the motor retainer, which both sustained no damage.
The simulation for the test flight, we overrode. We took a measurement of the center of gravity and the weight, and we overrode those in the simulation, getting an apogee of 10,205 feet on launch day. We were unable to verify how accurate the simulation was because we experienced this catastrophic mechanical failure. We ended up going to an apogee of 8,596 feet. So
the quadcopter and its retention system was flown on the test flight. The quadcopter was flown up until the point of release from its parachute, as we were not ready to test the autonomous flight controller yet for the quadcopter. However, the quadcopter and all its sensors were operational throughout flight, and the retention system was utilized. We had successful retention of the quadcopter throughout flight, and had successful deployment as well. And this image shows the quadcopter when we retrieved it from the landing site. We had a couple components that were 3D printed fail throughout the flight. The exact reason those components failed is not entirely sure yet. However, we believe for the unfolding mechanisms, a couple of them sheared, and we believe that this could be due to the faster than normal landing that the quadcopter experienced. This happened with one of the shroud lines tangling up in the arm, as you can see the bottom left arm in the image there. So this could have caused the quadcopter to land much faster than usual. All the electronics, sensors, and all those components were all functional and are still functional now after the flight. Sensor data was recorded. However, we received a erroneous IMU acceleration reading a couple minutes prior to launch. This caused the software to believe that it was actually in its launch state when it was still on the pad. And so the data that we recorded was the data while it was still on the pad instead of throughout the flight. However, this issue of removing outliers from our IMU detection system has now been accounted for.
So at the test flight, right before the takeoff, the GPS, we lost GPS data from the GPS, and at apogee, the altimeters read the altitude of 8,596 feet, and they fired the drogue charges successfully and deployed the drogue parachute. But at the same time, it's theorized that due to this drogue deployments, the tugging force on the shock cords accelerated the payload, which made it hit the nose cone and separated the nose cone prematurely, deploying the main parachute and the payload way before 800 feet and near apogee. And the CO2 ejection system, the black powder charges were fired at the main altitude, 800 feet. However, these charges were not enough to puncture the cartridges. However, we also learned that one of the biggest concerns with the system was that due to the acceleration and the vibrations throughout the flight, the canisters could puncture prematurely, but they didn't puncture at all. The rocket was recovered 2.2 miles away. It drifted 2.2 miles away. And the payload was also like about 0.5 miles away from where the rocket landed. And everything was recovered at the end. So before competition, the stuff that we need to work on, one of them is the CO2 ejection system. One of the reasons why we think that even though the amount of black powder was enough to puncture the canister on the ground was not sufficient while the rocket was in flight is because we think that due to the flight conditions, the black powder might have splattered within the volume that it was contained in, causing it to not burn at once. So we are going to store the black powder in a smaller volume, which was gonna make it like pack tighter and make sure that it doesn't move around and it's gonna burn at once when it's supposed to. The O-rings inside the CO2 ejection system are going to be upgraded to the ones that are resistant to temperature and corrosion. And more puncture tests on fresh canisters are going to be done to ensure reliability. And the premature nose cone separation, we're going to decrease the drogue black powder charge to reduce the tugging force because of the deployments. And we're also going to pack more shock cord for the forward section to make sure that the payload doesn't move around as much at ejection events.
With a quadcopter, the next steps are to complete the quadcopter tuning on our test stand. And once that's complete, we're going to begin free flying the quadcopter and complete any tuning in free flight, as well as conduct extensive flight testing in different flight environments to make sure that the quadcopter is stable, and also complete release testing from the parachute to ensure that it can recover from that free fall it will experience.
And then in terms of major structural components, the biggest preparation that needs to be done before the competition is the full rebuild of the aft following the previously mentioned epoxy aft concept. An additional airframe layup is currently being completed to replace the damaged aft. Manufacture of new centering rings made out of epoxy glass and wood is currently being conducted. Those will be secured to the new airframe once it's completed. The fins will be modified as necessary to accommodate the revised design, and all of the fasteners in the thrust plate sub-assembly will be replaced with fasteners that are more appropriate to fastening to the new wood centering ring.
All right, so that concludes the presentation that we had prepared from all of our leads. Thank you all so much for listening, and we can now open it up to for any questions that you guys might have. We're happy to go back through the slides, and then also the camera that we have mounted up here is a mobile camera, so we can move around and show you things up closer if you would like that as well.
Ben, you're muted still, honey.
There we go. That I was going to say that was a very good presentation. It looks like you've got a fair amount of work to do before the contest over the next 6 weeks, I guess, 7 weeks, whatever it is. If I understand things correctly, the first cut at retaining the motor basically didn't work. The fins came loose, sheared, or whatever, or at least our mounts did anyway. Maybe the fins didn't actually do that. And it's unclear to me what happened at Apogee, whether the payload quadcopter was actually released or not, and what kind of trouble it ran into. So if somebody could go back over and kind of describe from launch through Apogee, the test flight, and what went wrong, not a long dissertation, just kind of like a summary.
Yeah, for sure. So the rocket launched successfully off the pad, and we suspect that at during ascent is when the modular aft design failed due to the lack of structural reinforcement, which is what we expect caused the rocket to undershoot its apogee a little bit. At apogee itself, the drogue charges fired as they were supposed to. However, it was a pretty big ejection. It was a 3.5 gram charge, and the payload system is heavy and it's mounted in the forward airframe with our main chute. And what we expect happened is when that charge fired, the force of that charge caused the payload system to actually slam into the nose cone and shear those shear pins early. So our drogue and our main both ejected at apogee at the same time. And subsequently the payload also deployed and then released early as well, all at apogee. And then the altimeters fired again at 800 feet when they were supposed to for main for the CO2 systems, but the systems did not puncture like they were supposed to, which is what Khan discussed. And at that point, everything had already ejected anyway, so there wasn't any ejection left to happen. The drone descended the way that it was supposed to. It released from its container and descended down the way that it was supposed to. It was never intended to autonomously fly, so it just descended down to ground along with everything else. And then we recovered everything after the fact.
Okay. So I think one of the things you noted on the copter was that one of the rotaries was tangled with the chute.
Yes.
Do you have any idea how you're going to prevent that from happening again?
Yeah, our lead will come and discuss exactly the plan for that.
Yeah, so we're going to do more testing, manual testing for the actual payload, the quadcopter release from the container. What we suspect happened was essentially we want one end of the quadcopter to fall out of the container as opposed to the other end. If the correct end falls out of the container, then the quadcopter is able to swing open and the parachute is not able to tangle. However, we think that the incorrect end of the quadcopter fell out first. And so when the arms unfolded as they were supposed to, the shroud line then caught around that one arm. And so what we're going to do is the parachute shield, that 3D printed component on the container, we're going to extend it slightly so that the end of the quadcopter that we don't want to release first is restrained inside of the container. And that way the other end is forced to fall out first, ensuring that the quadcopter falls out in the correct orientation right away. It also could have caught when it could have tangled worse when it actually landed on the ground. We are not entirely sure as we didn't see it during the actual launch due to releasing near 7,000 feet or so. But that's what we expected happen. That's what we're going to do to try and fix that.
Okay, well, a couple more questions about the quadcopter. It looks like there needs to be a manual intervention from a ground station to activate it in some way. How are you going to see this thing? I mean, you're theoretically going to 10,000 feet. You're gonna drop down and deploy it at 1,500 feet. That rocket could be 1.5 miles out downrange. How are you gonna pick out this little quadcopter on this little parachute to control it? Or you don't need a line of sight, or fill me in on how you're gonna be able to manually control something that's this small, that far away.
The manual, so for the command to release, we basically just want to ensure that it's not, drifting over people, just in case something goes wrong. We don't want to endanger anyone. So as long as it's over, open land, and as long as we have a radio connection, we can communicate with it and send it that command. The manual control of the drone itself is fairly simple. It's mainly just to, in case it starts spiraling out of control, tell it to, emergency stop, or if it starts flying towards some sort of obstacle, like, in Florida, we have a lot of trees at our launch site. So in case it flew towards trees or like a group of people, like the spectators, we can, stop it and make it land, anything like that. And as long as it has a radio connection, it can, which our radio has, the XB Pro S3B, I think, has a range of at least a couple miles off the top of my head. So we don't expect that to be an issue. And again, if we do lose radio connection during flight and don't regain it, it will just drift under the parachute. It will not drop off into danger.
Okay. Has any of the team been to spaceport before?
No, this will be the team's first time attending.
Okay.
Other than you, Jimmy.
Other than Jimmy, yes.
Well, yeah.
He raised his hand.
Yeah, just kind of a word of warning. It looks like you're going to have to pay attention to this thing, and based on past experience, and how teams get grouped to watch the launch, there can be a lot of distractions around you. So just keep that in mind as you try to figure out how you're going to visually track this thing and make sure everything goes correctly. Okay. And Jimmy probably can fill you in. I think he knows what I'm talking about. Because we got rockets are sitting on racks. Yours not the only one, and they're going off right and left, and it gets very busy and very noisy and all that sort of stuff. So, I want to back up to recovery, and if you can go back to the slide that had the dimensions on the recovery harness.
That one.
Yeah, that was it right there. What's the total? Okay, I want to make sure I understand things right. What's the total length of the shock cord between the D-link and the, what's the total length of your shock cords, I guess, is the best way to look at it.
Okay, so for the forward section, the total length is 40 feet, and for the aft sections, also 40 feet.
Okay, all right. The diagram was a little, that's what I kind of figured it was, but I just wanted to double check.
Yeah.
To make sure we really weren't looking at 13 feet as a shock cord, for instance.
No.
Yeah. And well, you laugh, but we've already encountered it at least once. Then I've done ground station. Okay, so let's talk about the aft end and the motor mounts and the fins. If I understand things correctly, we're going back to a more traditional system where we have through the body tube to the motor mount, securing the fins, and big fillets on the fins and that sort of stuff. Is that correct? Or
Yes, that is correct.
Okay, lesson learned. Okay.
Yes, we plan to discuss improvements that we would like to make to the modular aft system in our technical report and talk about that system more, but it is going to require a bit of redesign, and in favor of attending competition, we decided to go to a more traditional design and focus on redesigning something for the future, farther in the future instead.
I think that's a very good idea, and I've seen designs like that you're talking about do work, but they have to be pretty hefty, and you know, you have to look at that motor you chose. The M2500 does kick pretty hard, so
Yes, we learned that too at the test
as you
flight.
found out on that
Yes.
end of it. So let me see my notes. You answered all the questions about the test flight. Are you going to try and do another test flight before the contest, or is that just too tight?
We will not be able to do another test flight before. We will be doing ejection testing over again to ensure the separation, but in terms of a full-on test flight, we'll not be completing another one of those.
Have you given any consideration to not using your homegrown CO2 cartridges ejection system and just go buy one?
Not yet. We're planning on doing more testing on it first. Like we discussed in terms of the plan to sort of test out some different methods to ensure that the puncture will be more reliable. If we're not able to confirm that, and you know it really is a sort of hazard, then we would consider something like that.
Okay, remember the clock is ticking, so
Mhm.
and in some cases supplies are short. So if you're thinking about doing that, I would try to get that testing done as soon as you can. And I know finals and all that other stuff is floating around, but nevertheless, you know, just as there aren't too many suppliers of that kind of equipment around, so
Okay.
the supply is not necessarily large at this stage of the game.
Mhm.
That sort of takes care of it. You got a lot of work to do between now and then. I can see that. So, I'll ask you, Wayne, do you have any questions, sweetie, or comments?
No, I think you about covered it. Very nice job on your presentation. And good failure analysis.
Thank you.
I changed my mind. I do have a question. So are you putting your swivels on the shock cord or on the parachute itself?
It's underneath the parachute.
It's on the parachute itself.
Okay. Like Ben said, that was a little confusing, you know, where things were, and you could have shown it as one long recovery harness and just shown where things were attached.
Okay.
Just that's, you know, that's not a requirement. That just is a suggestion for the future.
Lee, do you have any questions or comments?
I do. I've got some other questions about the failure mode. Did y'all get any data from the failure flight? And from it, could you tell if there was a moment where it started decelerating more than normal to isolate when the failure occurred?
Did you get anything like that from the?
No, the velocity data from the shadow loggers was not. It bases the velocity data from the barometer, and the altimeters don't really give us a very good velocity data. It's good for altitudes mostly.
Okay, but there wasn't any point in the curve. I guess what I'm trying to figure out is, you estimate, when do you think the failure occurred? My other question was, did all the pieces stay together and it just cracked in that area?
All the pieces did stay together. One of the fins was off upon recovery, but we expect that one actually was just kind of like hanging off and then came off on ground impact because it was right next to the rest of the rocket. But everything else was it was all in one piece.
Okay, I guess what I'm getting at, I'm starting to wonder if you might have had a flutter event and just enough to crack one of them, but not enough to take the whole thing out when it was decelerating. And Ben and Elaine, and you've probably seen more flutter failures in your time.
I've experienced flutter failures myself.
But since y'all have made these fins you made yourself, I don't know how stiff they are, or if one of the mounting wasn't as firm. I'm wondering if they might have, or in the flutter failure you've seen, if it's flutter, it takes everything with it, or if you have seen somewhere it maybe does a little bit of damage, just enough to do this, but then not take out the whole rocket.
I had a different experience than they did. I think I actually had foam fins that were covered with Ben, help me, Roselle. Ben, what
Right.
did we put on my level 3 fins?
Yeah, that was it. Yeah, that
And
was
they were
carbon. Yeah.
Yeah, so and they were bolted in place. Each fin had between slots of plywood, and they were bolted in place with wing nuts. Not a good choice if you have big hands, by the way. But when I didn't fasten one of them down enough, because of the wing nuts and the small space, I assume. One of them fluttered free and tore and took out another one. Now, they were easily replaceable once I got it out of the tree. But I think we switched from wing nuts to just regular nuts and some thread lock. But so I didn't see that any of your fins actually broke.
No, the fins did not break.
Yeah, so it still could have been a fastening problem, Lee, but I don't know that it was a flutter, because I think that if it fluttered, the fin itself would have broken as well as
Yeah.
I don't know. Jimmy, what do you think? I mean, would it have broken the part of the airframe where they were fastened like that if they were fluttering?
I'm not an expert on flutter. I try not to
Me
flutter
neither.
myself. Hey, I have another thought. The flutter maybe could possibly, but when I see the thickness of your body tube, if I did my math correctly, it's only 7/100 of an inch thick.
That's
Is
correct.
that correct? Even for carbon fiber, that seems pretty thin. So my suspicion is just a compression failure, because you have all the thrust of that motor pushing up all the weight in front of it, and that fin section is caught in between, and it's weakened by the fin slots. So that's just something to put on the burner as a possibility.
One thing to note, I don't know if it's very easy to see, and maybe we can show them this section with their camera, but the centering rings are completely in half, and then the centering rings are what has torn through the airframe itself.
Right.
So the
Okay.
airframe doesn't necessarily have too much buckling going on. There is some, but it's largely due to the centering rings failing.
Okay.
At least that's how it seems to look. And you can show them like this up here too. You can see these broken centering ring pieces.
Oh, wow.
Okay.
Yeah.
Yeah, so
Okay.
my thought is, as we put it back together, is there some other failure mode that will manifest itself with your new construction that you might want to compensate for before putting it all back together? That's
Mhm.
where I was going.
And if Jimmy's suspicion is right about basically a weaker type airframe, you could always, I hate to say it, you could always foam fill it.
Mm.
I hate to say it because it's weight and all that kind of stuff, but
Mhm.
you know, I assume you have done compression testing on your airframe tubes?
We did last year on the same layups, but we are making them again this year, and we didn't do it on this specific airframe, but like the layup itself had been tested in the past.
Previous designs did not have the slots that this current design has. With last year's design that they compression tested, the fins were not through the wall. So that is definitely a potential contribution to the failure, is compromisation of the integrity of the airframe when we actually cut those slots in. So that's
Okay.
something to consider.
Okay.
So I have two other quick thoughts. One is your switches for arming. You have this pin that's threaded through, and you're pushing those pins down. Those switches they may be okay, but the way they're mounted, hopefully they don't get activated with a G-Shock or G's. But since it didn't didn't appear to affect on your test flight, you may be all right. The other thing is when you put those, if you have to rearm it and put that pin back in, I don't know if you've tried to do that, but trying to thread a pin through it while it's on the mount and everything can be very difficult, unless you've got some guides in there. So if you've got guides in there,
Yeah. So the way that it's mounted is like lined up right in the middle of the pressure pore holes. And at the same time, I'm also planning on extending the guide that goes to the pressure pore hole so that it just slides in there easier.
And as built for the test flight, we had it that way and we were able to take it in and out.
Okay, good. My only final thought was you had that early deployment of the payload. You have a big shock event. You've got a lot of mass up there, and if you end up putting more more shear pins, make sure you reconsider everything going on with the ejection charges, and you don't fix one thing and cause another problem.
Mm-hmm.
All right, that's all I have.
Yeah, that's an indirect lead into how long the shock cords are and all that sort of stuff going on up there. So very good. All right, I'm going to reverse it. What questions do you have for us?
Do you guys have any questions you'd like to ask? We were not we did not know that we were going to get to ask questions. So just what is it?
I'm not that mean.
I know one question that we have had is there's been some varying announcements and information that I've heard about flying drones at the competition. Is there kind of a final word on what that's going to look like, what we're required to have to be able to fly the drone in terms of licensing or anything like that?
Yeah, to be honest with you, I have not kept up with the drones. The best person to ask for that and follow up is Andy, who I think you've
Okay.
already talked to.
I have, yes, I have.
Yeah. I think there was a lot of confusion within the organization in the early part of the year about drones and what was required in terms of licenses and what parts of the FAA regs you were going to have to follow and all that sort of stuff. And it took a little while to sort that out.
Okay.
But it's from what little bit I understand, a lot of the things we thought we were going to have to impose on the teams turned out not to be. That since you're not a commercial entity, the rules do change quite a bit. So
okay, that's good. Did you guys have any other questions about drones? No. Okay. In terms of for the competition itself, because since the team has not attended before, I know that you spoke a little bit about what that was going to look like. Is there any major things you feel like we should know going into a competition like this? Some of us have been to the student launch competition in Huntsville before, but never to spaceports. So we're just trying to keep up with everything and stay on track, to be able to get there. But if there's any just advice or things that would be good for us to know going into it, I'm sure we'd love to hear that.
Don't wear sandals or shorts. Bring lots of sunscreen and water. Black is a really bad choice. Big hats, wide brimmed. Lots of water. If you don't like food truck food, get a cooler.
Hydrate.
Yes,
Hydrate,
lots
hydrate.
of water and Gatorade or some kind of electrolyte drink. You don't have to drink a lot of it.
Gatorade.
Gatorade. Yeah, the other thing
if you don't like Gatorade, BioSteel's a good alternative, and they sell it at the grocery stores, either the packets or the thing. I think Gatorade is disgusting, Jimmy.
That's where Gatorade came from.
Keep in mind that you are in the desert. You're at roughly 4,600 feet elevation.
It's very, very dry.
Yeah, and the weather will range anywhere between 90 degrees and 120 degrees. And
unless it's like last year and it rains on you all day.
Yeah. Well, hopefully it won't rain this year.
Hopefully not.
Yeah, and obviously you need some sort of a canopy or a tent or
Mhm.
something to shade yourself, because you'll be
A
sitting up
tent.
in the same area as before
Oh.
with, with basically a tent type stuff, so.
Mhm.
And chairs, you do not want to sit on the ground there. There are fire ants, there are crawly things that bite. Don't sit on the ground.
Okay.
There is a medical tent just in case.
Yeah.
Most of the time, it's people who got too hot and didn't drink enough fluids, or they were black. Don't wear black out in the sun.
Right, recovery wise, you're dealing with sagebrush that's got 2-inch long thorns on it that will that will poke through your shoes. So, just basically
Hiking
you gotta
boots.
dress appropriately.
Yeah,
Mhm.
hiking boots, steel-toed work boots, something along those lines. So, and there are also snakes, and they have teeth too.
Yep. Welcome to spaceport.
Yeah.
Yeah.
In terms of before we go out for launch, in terms of the initial like readiness inspection and stuff like that, what does that entail? What should we be prepared for
You've
the
been to
initial?
SLI?
Yes.
It's gonna be like that.
Just like that?
You're
Okay.
gonna bring it ready to like launch ready without any propellant or energetics in it. And they're gonna have you take it apart piece by piece and look at all your hard points for attachment. They're going to make sure that all of your switches are labeled. Your primary altimeter, your backup altimeter, which is the main, which is your drogue. Oh. Make sure you know how to fold your parachute and that it's according to manufacturer's instructions if you're using a manufactured parachute. I don't know. What else, Jimmy? What did I miss?
I was gonna say, be able to discuss your charge sizes, your
Okay.
motor mounts, that sort of stuff. And they will ask you to take it apart, so
Yes.
don't
Yeah.
come there with your sure pins in and all that sort of stuff, because
Yeah.
it's just hard to take them apart, so.
Mhm.
And then that would, so.
And bring whatever tools with you that you need to put it together or take it apart.
Mhm.
If you need a screwdriver or a wrench or something like that, make sure you have a little bag of the stuff that you need to have it to take it apart.
Excellent. Thank you. Does
You're
anybody else
welcome.
have other questions they'd like to
Hey,
ask?
just one more comment. You mentioned a payload, but in reality, you're not really competing in the payload contest, correct?
We intend to.
They're not competing in the
You don't have the right form factor.
in the CubeSat form factor, but
No, not in that. No, not in
Yeah.
that.
Oh, okay. Okay. No, so in other words, no bonus points for the CubeSat format.
Right. No bonus points for the CubeSat, correct.
Okay. All right. Okay. All right. Unless somebody else has some more
Well,
questions, and don't be
one more.
bashful. Oh, go ahead, Jimmy.
Let me run this by you while you're both here. About the CO2 deployment and the failures, and wondering how effective that is. Would it be a good conservative approach to have one CO2 and one black powder, and have the black powder being your backup to save the bacon? Now, I know you don't want to fry your electronics, but we want to avoid a ballistic to recovery at all costs, or almost all costs.
Mm-hmm. Yeah, we did. In fact, we tested our CO2 systems on a smaller rocket prior to our full scale test flight. We tested it on my level 2 rocket. And for that test flight, we did have one CO2 system and one black powder charge. And so, once we do more testing on the CO2 systems, that is an option that we could consider as well.
Yeah. Okay. I just wondered if Ben and
good suggestion, Jimmy.
Mm-hmm.
Yeah, that's in fact, I've seen a couple of configurations come through where they're using black powder as the backup to CO2, which is a good way to go. Just protect your payload.
Yeah.
On that end of it. So okay. I'm okay with what we got here. Like I said, I think you got a lot of work to do before you get there, but that's not unnormal. I can't think of anything else. My team, Elaine, Lee, I think this is good. You did an excellent presentation. You told us exactly what we needed to know. And that's pretty good considering we didn't give you any guidance on that end of it. But it's kind of amazing because the teams are doing exactly what you're doing. Okay. So they're either going back through their PDRs or CDRs or whatever that they presented to, internally, put slide decks together for us and then have the ability to show us the rocket. So I think it's working out great. My main goal is to make sure that we head off anything before you get the safety check, so they don't say no. That's kind of the goal of this, is just to see where you're at and if we can help with any kind of heads up before you get there. So you're not scrambling to Walmart at the last minute.
Yes.
Okay. All right. Very good. Everybody have a good weekend, and we'll see you in New Mexico.
Great.
You
Thank
can
you so
stop the
much.
recording now too.
And thank
Yep.
you, everybody.
Bye, Jimmy.
Bye-bye.
Bye, Jimmy. Bye, Lee. Bye, kids.
Oh.